Bismillahirrahmanirrahim. Hello everybody. Nice to meet you today. I hope to finish the chapter 10 during this week, because this is maybe the last week. So in the beginning, to my great pleasure for Dr. Kamran to attend us. So you have to welcome him and make some greeting for him and for recording this video. So now we will start. We'll start this lesson. Chapter 10 is talking about magnetically coupled network. Magnetically coupled network. So in this lecture, so you have some learning goals. For example, the first one, we have to demonstrate and understanding some concepts like mutual inductance, coefficient of coupling, and returns ratio through some analysis for circuit with magnetically coupled components. The next point, we have to move to analyze the circuit with the voltage and the current. The last one, unfortunately, maybe you can deliver these lectures in the next semesters for any subject or in other courses, but it is not will not go through this one as an application for the magnetically circuit with ideal transformer. So, meaning we will not study this part. Maybe we will study it in another lectures. Here in the book, we can add from my practical experience what is the safety consideration during dealing of circuits with transformers. It is very, very important. You have to care some safety for the magnetically coupling circuit. So we have to add this one. It is not listed in the book, but I have to put it according to my experience. So first slides, we are talking about application of magnetically coupling networks. For example, if I ask you what kind of devices use the magnetically coupling circuit. So we have many of devices like power transformer. That power transformer is used in power system extremely to stepping down or stepping up the voltage and the current, and the power be the same in both sides. But here we can make some kinds of stepping down or stepping up according to the kind of transformers. If you look here, this is the shape of the current transformer. This is another with inside. So there are some higher and core inside, and there are two coupling coils, so called the primary and secondary, inside. Also, there are some kinds of magnetically coupling like current transformer. If you asked you, if we have a circuit with 5 kiloampere, how can we measure this current? So we have to have some kinds of coupling transformer, so-called current transformer. Current transformer transferring from high current level to low level. For example, 5 kiloampere can be reduced to 5 ampere only using this kind of coupling. Also, we have some another kinds like potential transformer. If I asked you if we have a power system with 500 kV or 700 kV, how can we measure the voltage? So we have to reduce this voltage to be measured. So in such a case, we have to apply some kind of coupling, magnetically coupling coils to reduce the voltage. So here we have some example. What else we have for magnetically coupling circuit? If I asked you what kinds of circuit do you know or the devices that apply magnetically coupling, do you have an idea about this one?
Current transformer.
It's okay, current transformer, voltage transformer, and power transformer. What else? You don't know? So, we'll move to the next one. So here, further self-learning. After finishing the semesters, you have enough time. You have to read more. So we have many of applications of magnetically coupling. And just if you click here, at each point, you can go to the link and you can read more and more. So let's go through what is the further self-learning. So in electrical motors and generators, it's very important. you have to study in the future the electrical motor and the generators. So this is based on magnetically coupling. There are some kind of inductive charging products. Also, there are induction cookers and induction system heating system. Also, we have induction loop communication system, metal detectors, radio frequency identification, transformer. We mentioned the transformer before. So, wireless power transformer is very, very important for your study to understand the wireless power transfer that is based on the magnetically coupling. Also, what kind of magnetically coupling, not magnetically coupling, but we generate some kind of magnetic field around us here. Look around you and see which devices we can get it that use some kinds of magnetic field. No. Lubna, Mira, around us here, there are some devices using electromagnetic field. Amphal, around us, it is not the desk, it is not a chair, it is not the whiteboard, it is not this one. In which place you can find it? This magnetic coupling coil. The lamp. The lamp, it contains some shocking coil that is very dangerous, this one. And maybe it's called some kinds of this coil is called a choke coil. This is inside the lamps. So without it, the lamps cannot will be damaged. Here, if you need more further reading about this subject and you are talented enough to read and to study more, this is a new paper in this topic, so-called circuit model-based analysis of magnetically coupled resonant loops in wireless power transfer system. Here is a link. You can go and read more deeply about this subject. So here you studied already the resonance, and today you will study the magnetic coupling. So together there is some publications that tell you more details about the new application in this topic based on wireless power transfer system. So you can go to this one and read more. So what's your previous study about this topic? Magnetically coupled networks. What is your previous study? So there are two laws. It's very important to understand it both. Ampere's law and Faraday's law. So Ampere's law, this is true. If you have coil and the current flows this coil, so there is some kinds of magnetic field. So the other is the Faraday's law. So Faraday's law, when there is another circuit close to the first circuit, there are some kind of magnetically coupling, so there is some kinds of voltage will produce due to linking the field. Simply, you can draw some thing like this one. So here, this is a magnet. Magnet, this is north, this is south. So here some kind of lines comes from north to south. So this is called magnetic field. So this is called the magnetic field. So in such a case, the same if we have coil like this one, and if we put some currents here, there are kind of typically field, magnetic field like this one. This is phi. So this is the magnetic field, and the so-called this is magnetic flux. So here for Ampere's law, you can apply if you have a coil, have current injected here. So this is some kinds of magnetic flux. This is Ampere's. If you put some kinds of any circuit here besides this one, so in this circuit there is output voltage will be reduced, output voltage GV. So there are some kinds of voltage will be reduced due to the flux from this circuit. So I have to get two circuits. Faraday's means two circuits, primary circuit and coupled magnetically with first one to produce voltage here. Ampere's law, this is just if I have current flows in this circuit, so I have magnetic flux. This is what means Ampere's law and Faraday's law, and you have to keep these two laws in your mind. It is very important. So what is the sequence of lectures? Actually, you have to write down in your notebooks. We have to summarize. These lectures will contain 5 points. And at each point you have to click, yes, I understand this point or not. So sequentially we'll move and we'll ask you if you understood already this point or not. So here is the sequence of lecture. The first point we have to explain how can you use the voltage in a coil. If you have a coil, you have the currents, how can you use the voltage? The next one, use the voltage from magnetically coupling circuit. If we put two circuits, how can you reduce or deduce the voltage in other circuit? So here's the third point, is that deduce the voltage from magnetically coupling with two circuits. If I have two circuits and this circuit are closed, so how can reduce the voltage in both circuits? Fourth one, what is the reason of dot marking? Some called dot marking, I will explain it. What does it mean, Turner's ratio? Also you have to understand this point. The last point, how to solve a magnetically coupling circuit with voltage and current to help you to enter the exam and to get the final marks. So the most important, the last one, the 5. How can we solve a magnetic coupling circuit with voltage and current? So you have to keep this one, and when I ask you, have you understood this one, you have to click yes or no. So this is the sequence of the lecture. Now we'll move to the first points. How can you use the voltage in a coil? How can you use the voltage in a coil? Simply, if you have circuit like this one, this is the current. If a current flows through a loop for a ring, so what is the direction of flux? Right hand, same, so this one. So the flux will go from up to down like this one. So this is the direction of flux. At this point, we have to keep in your minds two facts. If we change the directions of the current, the flux, what happens to flux?
Change.
Will it change? So the flux will change. What happened if we change the configuration direction of the ring? If you change the configuration, what does happen for the flux? The flux will, of course, if we change this one, this circuit to this will be 180. What will be happen?
180.
This is also the flux will change. So keep this in your minds. When it changes the currents, the flux will change. When it changes the configuration, the flux will change. When it changes the current, the flux will change. When you change the configuration, the flux will change. So I have two terminology. The current direction will change the flux. The configuration of the circuit will change the flux. It's okay? So here before this one, let's go to the lectures. How can deduce the voltage in a coil? To deduce the voltage in a coil, there are two terminology. If we have circuit like this one, and here the current I, this is the inductance L. So you have to keep in your minds two equations. The first equation is talking about flux linkage that depends on L, I. And also we have another formula for the flux linkage, so-called lambda equal, if I have one term, so lambda equal phi. If I have n terms, so lambda equal n phi. So I have two flux linkage, Li and n phi. Li and n phi have two flux linkage, Li and n phi. Li is used to the voltage, self voltage on the coil. If you are going to calculate the voltage, so you have to use Li. So this is for self voltage in the circuit. When you use lambda equal n phi, so you have to have another circuit. You have to have another circuit, so-called magnetically coupling, and reduce the voltage from other circuit. So here, when we are going to reduce the voltage, so this is mutually coupling the reduced voltage in another circuit. Let me conclude once more. Now, if we change the current in the circuit or in the coil, what happened for the flux? The flux will change. If we change the configuration of the coil, what happened for the phi? The flux will changes. Here we have coil current amperes tells us if the current flows in here, so we can deduce the voltage. But this is the theory of Faraday's. So ampere, if I have current and the flow, there is some magnetic field. If we put another circuit, so we can deduce the voltage in other circuit. So I have two flux links. The first one, it depends on Li, and this formula is used for self voltage in the circuit. And the other is lambda equal n phi, and this is should you have another circuit to be coupled with the first circuit to reproduce the voltage. So we have two terminology, lambda equal Li, and lambda equal n phi. Lambda equal Li, and lambda equal n phi. This is used for self, this is for used for mutually. By keeping these two in your mind, it will be easy for the derivation, all the slides which will come now. So let's go to these slides. So here we are going to deduce the voltage in a coil. So simply, if I have coil like this one, if I have coil like this one, and there are currents here, and I have LE, so what is the voltage? The voltage equal L di by dt. Voltage equal d lambda by dt, d lambda. Which form will use to deduce the self voltage? The first or the second one? The first one. So we will use lambda equal Li. So we can replace this one, lambda by Li. So the derivative is L di by dt plus I dl by dt. This term is constant, so equal 0. So the self voltage on the coil equal L di by dt. The self voltage on the coil equal L di by dt. Self equal L di by dt. No, the self L di by dt. L di by dt. So this we finished from deducing the voltage in a coil. This is the self coil. There is no any mutual. So now we'll go. Have you understand already the first one or not yet? Clear?
Yes.
Deduce the voltage in a self. Self voltage. It's clear?
Yes.
Yes. So this is clear. It's okay. Let's move to the second part. If we have two circuits, one of the circuit, of course, will be closed because we need the current flows from here. And the other circuit is open circuit. Open circuit. So we will apply here Faraday's law. If you have magnetically coupling, how can we deduce the output voltage in the second circuit? But here there is no load. So the current here is 0. This is open circuit. So we will deduce the voltage. Do you expect to use lambda equal Li or lambda equal N phi? N phi. So if there is magnetically coupling, we will use lambda equal N phi. So first let's finish from the first one. In the first one, if I have current, I have L. So what is the self voltage here? Equal LDI d lambda 1 by dt equal L1 di1 by dt. And this is the self. What other the circuit V2? So looks here, for the first circuit we have flux. Flux will go to the mutually with the other circuit here in the 2. So some kinds of this flux will be linked by the other circuits. So we can deduce the other voltage here from the second formula, lambda equal N phi. Which kinds of N? To use this N or this N? I will use the number of turns which will cut the flux, because this is transformer here. So how many flux is cut by using this N2? So this is the flux comes from the first one equal N2 phi. So lambda equal N2 phi. Why N2? Because this is the circuit which will cut the flux comes from the first circuit. So here we will use V2, the voltage deduced from the second coil will equal d lambda 2 by dt, and lambda 2 equal N phi, which N? N2. So N2 and the phi comes from the first circuit. So it is easy to use this one. So what about the phi? Look here, if we divide both, the phi will equal Li over which L? So phi comes from here, which L? L1. Which comes from a, which N? N1. So phi, I can replace phi by L1, I1 over N1. So if we take this part, N2, L1, N1, and we put it as shown in this slide, so we'll call this one L21. What is L21? L21 is the mutual coupling. Is the mutual coupling. This is the terminology that we mentioned before. L21 is the mutual coupling. It depends on what? L21, so the voltage here will equal L21 di1 by dt. So L21 is based on N2 over N1 multiply L1. So the reduced voltage due to Ampere's law equal L21 mutual inductance multiply di1 by dt. So and the L21, it is what is the formula? It equals N2 over N1 multiply L1. Clear? So here we have open circuit. I have the first circuit, I have the second circuit. For this circuit, I can reduce the self voltage, which comes as V1 equal L1 d1 di1 by dt. The second voltage will open the circuit equal V2 equal L21 di1 by dt. It's clear? So we have self and we have mutual voltage. We have self for the first circuit and we have mutual voltage for the second circuit. Is it clear? So we have here N2 by N1. This is so-called Turner's ratio. Some kinds comes as N2 over N1 or N1 as N2. This is the Turner's ratio. So now you understood what does it mean Turner's ratio. You understood already what does it mean mutual inductance. So here I talked in the beginning, we have a problem in the safety. This is one of the learning points. When you're dealing with the magnetically coupling circuit, you have to care with the safety. What is the safety consideration here? Look to this equation deeply. This equation depends on N2 or N1. For example, if I select N1, very few turns, one turn, two turns, and I select N2 very large number of turns. So what is the value of V2? V2 will be very high, and this is the theory of current transformer. We mentioned some application. Current transformer, it uses very few numbers of turns N1, large number of turns N2, so the output voltage will be very, very large. So if you leave the circuit open and put it, this is number, few number, and this large number, so there are very large voltage can burn you and burn your body once you touch it or touch it or you put your hand here. So it is very, very dangerous if you put your hand. So for these reasons, when we have current transformers on the line, when we use it for measurement, you cannot leave it open. When you leave, for example, you can measure, as an example, if you have something like this one, and you have here this one, and here we have the device to measure the voltage. So if we leave, for example, for any reasons, leave this device, so it is very dangerous if someone touches this terminal. So in such a case, you have to put here like a switch. If you remove this one, this switch will be closed as a short circuit to protect the persons. If you leave it open, very, very dangerous and will burn you. So once you leave the measurements or this device, so you have to close this one. For this reason, you have to be careful with the magnetically coupling circuit. In case of current transformer as one applications of magnetically coupling. So this is the reason or for safety consideration in this point. So now let's conclude this part. If we are going to calculate the self voltage, so the V1 equal L1 VI1 by dt. This is self voltage. So the mutual voltage V2 equal L21 mutual inductance di1 by A by dt. Have you understood this part, or once again we will back it? Clear? Clear? Clear. So you can put here. Clear. It's okay for this part. Let's go to more complex circuit. So we finished from the first part, one circuit, two circuits with the second circuit is open. Now we will close both circuits. We will close here. What we are going to get? We are going to calculate the self and mutual. The self and mutual. So I have two coupled circuits, and I have two sources, I1 and I2. And in both circuits there is magnetically coupling. So if you look to this circuit, so we have self voltage. And if the current flows here, so there is some kind of mutual, so there is mutual voltage. If the current moves here, flows here, so in such a case we have self voltage, and we have mutual voltage from other sides. So it's simply we can put lambda 1 equal mutual, as we mentioned before. I have two terminology, so L1 I1 this is used for self, and I have L1 2 I2. So lambda 1 here, so it depends on L1 I1, and the mutual comes from the other circuit, so L1 2 I2, and L2 equal L2 1 I1 plus L2 D2. So finally we can make derivative for the d lambda 1 and d lambda 2. So at the end I have voltage here. The voltage is the first part is the L1 di1 by dt. This is the self voltage. What is the mutual voltage? Assume the mutual is L1 L1 2 di2 by dt. And what is the second voltage here? Second voltage here it considered as L2 di2 dt as a self voltage plus the mutual one di1 by dt. This is for the two loops, closed two circuits, closed circuits. So I have two parties. This is so-called, this is the self part, this is the mutual part, comes from this circuit. And here, when I calculate the voltage, it can be L2 di2 by dt, the self, and the mutuals comes from the secondary circuits. Now, if I have two closed circuits, so now the V1 and the V2 equal the self part and mutual reduced part, and V2 equal self part, and the mutuals comes from the other circuit. So, keep your mind, we can here L12 and L21 equal M. This at your home, try to say why we put L12 and L21 equal M. M is called the mutual between the two circuits. So here we assume L12 equal L21 and M, and at home you have to search about what does it mean to both M equal L12 and L21. This I will leave this part for you to read it at home. So now, if I have two coupled circuits with the closed loop, I can reduce the V1 and the V2. So, for two magnetically coupling circuit, have you understood this part or not yet? Sally? No? No? Yes. So we have to move to other part. Have we covered the turns ratio? So we can turns ratio. So let's go to the dot marking. Call back what you put in your mind. What you put in your mind is what? If the direction of the current changes, what does for the flux? If the configuration changes, what happens for the flux? Will it change? So now we study if we change the I and if we change the configuration. So here simply, effect of current direction. If we have, this is the first circuit, and the second circuit, if we reverse the current. If you reverse the current, what's the case of the flux? The flux will change. So in such a case, we can put lambda 1 equal L1 I1 minus M1, and L2 equal minus MI1 plus L2 I2. Keep in your minds the self is the same. It doesn't depend. When you look to the circuit, the self doesn't change. If you change the voltage, the self voltage is the same, no changing. But the mutual coupling depends on the direction of the. So if we reverse current, so this mutual coupling will be reversed. So it is simply V1 equal L1 di1 by dt minus M di2 by dt. So we can put minus here. So V2 equal L2 di2 by dt minus M di1 by dt. It's clear? So if we reverse the current, so here the mutual will be negative. Same. Here, these two circuits, if you are making this coil like this one, what happens if you change the directions of making it like this one? So here I changed the configurations of the turns. So here I have a problem. Now, as I told you in the beginning, we have a transformer, and the transformer is totally enclosed. So how can I know if this winding like this one or like this one? So we have different configuration. To recognize this configuration, we have to put dot. We have to put dot. Dot is an indication for the directions of coil. Maybe in this direction, maybe in this direction. So if we change this direction, the flux will change. If we keep it like this one, the flux is the same. So we can put some kinds of indications as dot to indicate the configuration or the structure of the winding. So this is the reason of putting the dot. Look here, for the first circuit, we reversed the first circuit. If we reverse the first circuit, we will keep the same turns ratio in these directions. So here we have two circuits. We can keep, if we have the winding like this one, so we can put here dots and here dots. So we have the current IN1 and I2, same direction. I have put two dots. This two indicates the configuration is like this one. And if you change the configuration, so we can put like this dot. If you change the dot, so what's the case of the flux? The flux will change, and accordingly, the mutual will be negative. So in first case, if we keep the same configuration for the dot, so we can obtain like this one. For this primary coil, L1 equal di1 by dt plus mutual positive signal here, Mdi2 by dt. The second circuit, V2 equal Mdi1 by dt comes plus safe voltage L2 di2 by dt. If you change the configuration of the turns ratio and we put like this one, so we have negative sign for the mutual. Let's just conclude. If you have this shape of coil direction, so you can keep this one. If you change it this one, how can I know? So we can put it like this one, opposite direction, so we can keep it with negative mutual coupling in between. Now, it's very important to understand. Now I have, as we mentioned here, and keep in your mind, if I change the current, the flux,
It will change.
if it changes the configuration, the flux
It will change.
will change. It's very, very important to focus. So let's ask in the first example to keep it as this one, I1 and I2. So if I am going to calculate the voltages at these sites, so I have these two coils. It is like in same directions as we plotted before. So the dots is the same. So we have L1 di1 by dt plus Mdi2 by dt, and I can put positive, negative, positive. The other circuit, if I put this one, so we can keep it as this L2 di by dt and Mdi di by dt and plus. If we change this one and keep the currents the same, so we will change the mutual coupling here. We will change the reduced voltage from the coupling here. So we can understand that if we leave the same dots and the same currents, so we can keep this equation. If we change the dots, so we can change only the mutual coupling here. Have you understood the dot marking? Have you understand why we put dot marking to indicate the direction of coils, as inside or outside? Yes. It's okay. Now, basically you understand the first, second, third, fourth. So we have to solve some problems according to what we explained now. So it is very important for you. Now, maybe face a problem. Now, what is the problem? When you put this one, so now if we ask you to calculate V1 and V2, so we don't mind about V1 and V2, so keep this one, and keep this one. So look to the dots, and look to the currents. Current, we explained before, same current in system directions, and we explained before the dots as we explained here, it is typical the same. So if the current flow in this one, the current flows in this one, so I have to go to calculate the voltage here and the voltage here. If I ask you, the mutual will be negative or positive?
Positive.
Why positive? Typical dots, typical direction. It's not reverse. It's okay. Typical current flow in the circuit as we explained, and the typical dots. But when Dr. Isa or Dr. Ibrahim or Dr. Mahmoud are trying to lay in the directions of the currents, for example, the current comes from here, and the modes of A dots sometimes here and sometimes here, will be very totally confused for you. So we have to learn rule. And the rule can help us, how can we drive this circuit easily. So I will give you very straightforward rules. Through these rules, you can solve any problem. You can solve any problem. But if we depends on the currents like this one and this one, and if we change this, for example, the dots here, it will be totally confused. So we have to learn something as a guide that help you to get the fall, and this is the most important for you. So let us give you let us conclude. It is very, very important really to understand the following. So if we have something like this one, as you know, this is dots and this is dots. So now I am going to drive the voltage here. So the self voltage is straightforward, no problem. The mutual is not a problem. MDI, but the problem in sign, positive or negative. You understand? The same here, V2. For the self, this is straightforward. L2 di2 by dt plus or minus MDI1 by dt. It's not a problem. Huh? But the problem in sign. So the most important is the sign of the mutual as being positive or negative. So it is simply, if I have assume any direction of current here and the current here, for example. So now the current enters the point or leaves the point? Enter. When the current enters the point, this is a positive. This is a positive. Positive for what? So if we assume this one, I1, and we assume this one, I2, and they have mutual in between. So if this is positive, simply you can put positive, negative, and positive in M, dI1 by dt. Clear? So M dI1 by dt is positive. When the current enters this point, when the enter positive or negative?
Positive.
Positive. You can put here positive, negative, M dI1 by dt. It's clear. Huh? Now, let's go to another example. If you have something like this one, here's a dot. Assume I1. Assume current comes from here. It's okay? First, if the current enters to this point, positive or negative?
Positive.
Positive. So this positive, negative, M dI1 by dt. Here, current enter or leave the dot? Leave. What does it mean, leave? Negative. So put negative here. So negative, positive, M dI1, dI2 by dt.
That one is di2. The top one di2.
dI2, dI2. Yes, correct. Let's go to another example. Here. If you have dot here and you have dot here. So if the current in a direction, I1 is the current there, for example, I2. So here the current enter or leave? Enter the point. So here
Positive or minus?
here's the current. Enter or leave?
Enter.
Enter the point. So enter the point, positive or negative?
Positive.
Let another example. If the current leaves the point, positive or negative?
Negative.
Negative. You have to what here? What negative? Positive. M D I1 by dt. Here. Leave the point. Positive or negative?
Negative.
Negative. And this is positive. M dI2 by dt. It's clear?
Yes.
Let's go to the example. This example very simple. So I have to forget the calculated voltage V1 and V2. Look to the currents. Now the currents will flow to this, leave or enter the point?
Leave.
Leave. So here,
Minus.
what about the self? It's the same, no change for the self. What about the self? What about the self? It's the same. Look here, the current
Leave.
leave. So here,
Minus.
minus positive. So minus MDI by dt. So here, assume V1 minus V1 equal this one. So V1 equal minus minus. This one. So here V2 equal plus. Is it clear? Is it clear? Happy? Assess your learning. If you understood what I mentioned, so please go to this example. Here, V1 and here V2. Look here, there's no current here because it's open circuit. Huh? No current here, there's open circuit. So, for the first one, give me the results. Assess your learning to go to complex problems. What about I1? What's is the other side? V2 equal? M di 1 by dt. It's okay. Look to the other. Positive, negative. V2 equal? Positive, negative. Equal voltage equal? Positive, negative. Positive M or negative M? Positive, negative. What about the V2? V2 equal? M? Positive or negative? Negative. Negative M. Positive, negative. So here's the current. Leave. This negative. This positive. So V2 equal? Positive, leave, negative M di1 by dt. Here, the current leave equal minus positive. V2 equal positive M. It's clear. So this is the answer. Positive, negative M. Clear? It's very clear. No doubts about it. It's clear. So let's explain. Sometimes the student confused with the polarity, like this one. If we, for example, I asked you this one. If I asked you what is the voltage applied here and what is the voltage in the other sides, so as we mentioned, it is not a problem. So if the current enters this void, this will positive or negative? Positive, send signal here, positive, negative. And what?
Minus.
Sometimes when we have complex circuit, the student confused with this one. So we can replace this one by current source. It's very easy and straightforward. You can put your equation easily. How does it come? If you have, instead of writing this one by this way, so we can easily replace this one by current source. So here is positive, negative. So I can put here current source. It's very easy. Positive here, negative. What is the value? M di1 by dt. So in this such case, I can remove this one. So like when I ask you about What is the voltage here? It is easily minus MDI1 dt. So instead of writing M by polarities, so we can replace M by polarities by current source, voltage source. So here the current leave or enter, leave positive or negative? Huh? Negative, this is positive. Negative. Negative. Huh? Positive, negative. M di 2 by dt by dt. So the current source, it is very easy to be considered in the circuit instead of writing M here. And instead of writing here minus M di 2 by dt, it will be very confused for you. So we can replace it and what? Minus, positive. Minus, directly you can put in positive, negative, and the current A, current source. So it is very easy to calculate here the voltage V1, and it is very easy to calculate the voltage V2. So you can, you learn it in all the sections, the current source. So in this case, the current source will be negative. Here the current source will be negative. But if we put minus M like this one, it will be a little bit confused. So we have two ways to replace it by voltage source, dependent source, or you can put it as M di1 by dt. So let's go this one. It's very simple. If we put this, will go to apply, enter the points. So the other side positive, negative, negative, positive, and M di. So very easy. V1 equal M di1 by dt as a positive. Huh? Here is the same. If we have current enter this point, and the current here enter positive. So negative, positive. So I can consider easily V2 equal minus. This one, if I have the current leave, leave, it is minus, minus. So this is positive, negative. It will be easy to calculate. So and it's the same for the last one. It's very straightforward. So now we have two ways. Let's also go very complex circuit like this one. So forget this one. So you have to understand first. Let's go step by step. Let's see how can we solve it, and I can assist by another example. Look here. We write mesh equations using the assigned currents. You see, mesh equations. We need to write the mesh equations for both circuits. So we are dealing with. Do you remember the first lectures? We are dealing with the time domain. This is the time domain. This is the time domain. I1 was a function of t. So we are dealing with time domain. So for this reason, we derive equations with di by dt. This is a new one. So we are going to explain in time domain. I1, so we have to make some kinds of them. Here, the problem in the whiteboard, not in the pen. Plus minus V1 T. So here R2, L2, L1, R1. It's okay. And there is some kinds of mutual in between called M. Something missing here. Something missing. Dot. We should drive in which dot. We are making the point. So excellent. There is dot here and there is dot here. So assume the currents in any directions. We'll respect this one. So here, I1, and in the same direction, I2 of t. It is very, very simple to drive this one. So, which one you are going to apply? Dependent source or with plus minus m?
I think plus minus L is
Mm.
little bit easy.
So we'll go with this one. So here I have current locally. Current, only the current I1 here will enter this point. But this point,
When we leave and I do.
not so. In which direction I will go? I2 minus I1 or I1 minus I2? Me, I will consider.
I2 minus
Me, I will consider I2 minus I1.
yes.
And I leave you to try what's the case if we change it, I1 minus I2, if there is a changes or not. So here, what is the input current? I2
Minus I2.
minus I1. And it's a dot here, I1. So simply, if the current here enters this point, so here, positive or negative? Positive. M, D, I1 by dt. So what is the case for this one? The current enter here, I2 minus I1. So current enter for this point. Positive or negative?
Positive.
Or so positive, here, positive, negative, M, D,
The I2.
I2 minus I1 over
DT.
dt. It's very easy. Kirchhoff voltage law. V1 of T. So in such a case, this is you will consider as voltage drop. And when the current, when you go with the flow, so when you go enter the X, so it should be positive. If we leave X, it will be negative. If we consider dependent source, it will be considered as a source. So you have to apply the source. So here as a voltage drop. So it is very easy. So V1 of T, let me consider this one. Is this positive or negative?
Positive.
M D I2 minus N1 over dt. This one positive or negative?
Negative.
Excellent. M D I1 by dt by. So now I finished from the mutual. What about the self? R1 I1 L1 DI1
DT.
by dt. L2
The I1. The I1.
DI1 minus I2. DI1 minus I2 by dt. This is the first. What about the second? If there is any kind of voltage source, no source. This is zero. We have to move in this direction.
Plus.
Positive or negative?
Positive.
DI1 by dt plus R2
I2.
I2
DT.
plus L2
L1. L2.
we are going with the flow. D I2 minus I1 over dt. No more. No more. So now, as exercise, you will try if we change this direction. What will happen for the same equations or will it changes? For your hand, you can try now for 5 minutes. If we change this direction, if someone assume the current will go from I1 minus I2. Solve as a group to gain time. Happy. Solve as a group to guarantee the marks of the final chapter. Solve as a group. quickly assume the direction of currents, put the inertia, تمام. assume I1 minus I2 I1 minus I2 dt. It's excellent. Yes. Of course, but you have to multiply this one inside. So you can get I2 minus I1. It's the same. It's okay? It's the same. Multiply inside. It's the same. So what is minus M in the I1? So if we change the direction by considering the I1 more than I2, it's not a problem. So I can solve for you. Yes, it's clear. Have you finished now? If there's any change in the equation, or the same? Almost the same. If there's any change,
I think no.
if you multiply this one, so this will be I2 minus I1. So it's the same.
Yes.
Understood. تمام. تمام. Put that in the side, multiply. So I2 minus I1. So it will be the same. It's the same. Feel free to make any changes. The most important, the current E, the current L, the current E.
Same definition.
Yes, it's the same. You can both change the direction to both in. So you can, it's very easy. The most important to respect leaving the dot or entering the dot. No, it's clear. If there is any change in the two equations,
No.
never. So feel free to put the current in any directions, apply what I explained to you about the leaving or entering the dots, and you can put the directions of positive or negative for mutual coupling, and if you to only write down the equations. It's okay? So now we will move to another example, but first, to make your mind relaxation for your brain, I will show some video about the transformers and about the power transfer to refresh yourself before going to this example. One of the magnetically coupled network application is the transformer. So you can see
in this video, we will go through the working and construction of a three-phase transformer by starting from its simplest form. The basic working principle of a transformer is simple: electromagnetic induction. According to this principle, a varying magnetic flux associated with a loop will induce an electromotive force across it.
this is what explained.
Such a fluctuating magnetic field can easily be produced by a coil and an alternating EMF system. A current-carrying conductor produces a magnetic field around it. The magnetic field produced by a coil will be as shown in the figure.
This is according to
With the fluctuating nature of the alternating current, the magnetic field associated with the coil will also fluctuate. This magnetic flux can be effectively linked to a secondary winding with the help of a core made up of ferromagnetic material.
Newton, Faraday's law.
This fluctuating magnetic field will induce an EMF in the secondary coils due to electromagnetic induction. Since the turns are arranged in a series, the net EMF induced across the winding will be the sum of the individual EMFs induced in each turn. Since the same magnetic flux is passing through the primary and secondary coils, the EMF per turn for both the primary and secondary coils will be the same. The EMF per turn for the primary coil is related to the applied input voltage as shown. As a result, the induced EMF at the secondary coil is expressed as follows. This simply means that with fewer turns in the secondary than in primary, one can lower the voltage. For the reverse case, one can increase the voltage. But since energy is conserved, the primary and secondary currents have to obey the following relationship. Three-phase transformers use three such single-phase transformers, but with a slightly different coil configuration. Here, the primary and secondary coils sit concentrically.
Magnetically coupled, huh? Inside each other.
Two more such windings are employed in a three-phase transformer. Transformers with high power ratings generally employ a special kind of winding, known as a disc-type winding, where separate disc windings are connected in series through outer and inner crossovers. The low voltage windings are connected in a delta configuration, and the high voltage windings are connected in a star configuration.
Just the star.
Thus, the line voltage further rises to root 3 times at high voltage side. This also means that, from a three-phase step-up transformer, we can draw 4 output wires, 3 phase power wires, and 1 neutral. High voltage insulated bushings are required to bring out the electrical energy. The core of the transformer is made of thin insulated steel lamination. Such steel laminations are stacked together as shown to form 3-phase limbs. The purpose of thin laminations is to reduce energy loss due to eddy current formation. The low voltage windings usually sit near the core. Various kinds of energy loss happens while transferring power from the primary to secondary coil. All these energy losses are dissipated as heat. So usually the transformer is immersed in a cooling oil to dissipate the heat. The oil dissipates the heat via natural convection. Oil in the tank will expand as it absorbs the heat. A conservator tank helps to accommodate for this volume change. To know more on different types of transformer cores and windings, please check out our other videos. Thank you.
Thank you so much. So here another application you have to understand.
Nowadays, when it is time to charge your phone, let's
It doesn't know. Sorry. It's 110. I would like to design some wireless power transfer. Current, flux, links other circuit, so reduce voltage. Understood the video or not? If the two coils perpendicular, no link into the flux, so the circuit is off. We need FY piece like this one. So now you understood the concept of magnetic current, so you can try ideas about it. two applications. So the students who will go to the power system, so enjoy it was important for electronics. You can go to so it's okay. So I will. It's back to the lecture. So this is an example. Topic. No problem. So, as explained here, this is the solution. It's two methods. And this was the case if we change this I1 minus I2. Huh? This is what explained now. So you have the answer and you have the. So, I think so. This is very easy circuit. Can you drive the two voltage V1 and V2? It's very easy. So here is the current here, enter this one. So here, positive, negative again. So here is the current, here is that. So positive, negative, and so on. So it's very simple. So now, how so magnetically coupled the circuit with what? Have you understand this one?
Yes.
So it's okay. So this is the last one. So now check this one. So you can move to another example. It is very important. This is very straightforward. Very straightforward. No problem. Look to this. We drive in the previous part. Two equations in time domain. In time domain. This is the same typically for the phasor domain. This is the same. So if we are going to apply for the phasor domain, so it is very easy. So this is the voltage 24 angle 30. This is 2, which are coupling J2. This is the capacitor. This is the resistance. So same concept. If the current flow from here, so this is enter, so will be positive, negative, and you can add in such a case J2 I1 J2. Now the mutual is J2. It is the mutual. It is like inductance in here. So you can put JM. So J2, the voltage here J2 I1. So this current leave. So here negative, positive. J2 I2. So you can derive the two equations. It's very simple. The most important to consider the currents. And also here the same. As we explained before, we will have current I1 here, I2, I3. So we can assume as you like. I1 minus I2 or I2 minus I1. So you have to consider this one. And in the same case, here I3 and I2. So you can consider I3 minus I2 or I2 minus I3. Any assumption can go. So here, if we assume I2 minus I1, so here we'll leave. So this will be negative, positive, the value. And here we can assume I3 minus I2, so we'll leave. So here I2 minus I2 multiply J omega. Is it clear? So the concept of using the direction of the current is the same. You can assume I1 minus I2, I2 minus I3, or I2 minus I1, I3 I minus I2, and consider this one, and you can take 3 loops as you have the solution. Is it clear? There's no problem. It's very easy, no problem. So now, if there is any questions, if there is any confusion, is it clear for you?
Yes.
Clear?
Yes.
Can you guarantee the format for this problem?
Sure.
If there is any questions, so please next Thursday there is exam at 12 o'clock. It's okay. And also you have to collect your projects from my office. Yeah, thank you so much for your attendance, and you are welcome if you have any problems. At the end, I would like to thank so much Dr. Ray Kamran for, I think so, you did